Hey, how y'all doing?
Good, how are you?
You know what? We've got today, tomorrow, and a test. So I'm feeling pretty good in a lot of ways. There is the trouble of writing a test and then I have to grade them. But you know what? Right now, it's okay. And yeah, today is the one last chunk out of our textbook, chapter 11 content. The lab associated with today, I did a minor rewrite of it to include interactions in an auto magic fashion rather than doing by hand. So I hope that that works out real well. I tried it myself earlier today and I thought it worked. But if you do have questions about, how to get the software to do a thing within the lab, definitely send an email, because that rewrite might cause you to say, hold on, this is unclear. So I want to fix that clarity, lack of clarity thing if there is a problem right there. I want to get that done real quick. I'm going to grab a screen in front of you, and there's something in the chat. Oh, it says good. Yeah, I like that. Okay, so share screen and that one. Boom. Okay, so just to draw your attention to where we're at, where we're going. If I was looking at our week 5 here, we're going to do variable selection today. Yesterday was quantitative factors, fitting with polynomials, etc. Tomorrow should be logistic regression, and then Thursday review. Now, that's all if things go as I'm planning today. If tomorrow, as a group, you've got a bunch of fairly good questions and want to talk about them, we don't need to go too much into logistic regression. The lab activity for that is such that I can alter it on the fly while in class. So if you decide as a group, you say, we want to tackle some subject matter questions, right before the lab, we'll do that first. And then depending on how much time we have, you'll be working on the lab, but maybe only a portion of it. Okay. So any questions on administrative matters other than, yes, labs, I have to yet to go through and finish all of the checking of those grades. And so it's likely that many of you still have several lab scores filled in as, yeah, I didn't do it. because I need to go back and check. And I think the other class that I'm doing this summer, they all signed up for their own groups, for lab groups, and it worked out brilliantly for them. And so I think there's some difference in the setting between you guys and them. So with that in mind, it means more work for me, but it's not a big deal. And it's because you have all participated and you got your name on it somewhere, or you sent me an email about that. It's just a matter of filling in the missing values, and we should be just fine. Okay, also want to draw your attention to another thing, the sample final exam. Yeah, that's what I hope to spend some time talking about on Thursday. And then the final exam, both parts will be open on Thursday. And so you could take them both, I think an hour and a half for each one. And just make sure you have enough time to get it done before the actual due date, which is like 11:50, 9 p.m. on Friday. Most people can work their lives around that. And if there's an issue due to something that's unexpected, let me know. I know that in some cases, there are people who are like, I'm stuck and it's in traffic and there's nothing I can do about it because, traveling. Let me know. We'll work it out. It'll be fine. Okay. So any questions on administrative issues? Okay. How about questions on subject matter content from yesterday? Okay, well, let's move this over here. And let's talk about the context of trying to build a model in a situation where you have lots of data that are collected, many possible explanatory variables. How do you figure out which ones to use or which ones to not use? Here's an example, and I'm going to use it a fair amount in class today. So let's just get in there real quick. I might like to know if the mortality, again, from air pollutant related, or I guess breathing related deaths, if the mortality from, breathing, like I have trouble breathing, so I died, if that's related to hydrocarbons, nitrous oxide compounds, or sulfur dioxide rates, and these are in parts per million in 1972, measured across these 50-some cities, 60 cities in the US. And due to an earlier analysis, I'm thinking the log of each of those explanatory variables, log of parts per million, seems to do a better job. And so I'm considering those three as explanatory variables. But we know from our earlier discussions this term, if I have an explanatory variable and I use it, it could reduce mean square error enough that I'll now be able to spot something that earlier I could not see. So maybe there's something in precipitation, humidity, January temperature, July temperature, over 65, housing stock, non-white poor, density, sound housing rates, etc. Maybe there's something in those variables that could be used to help us explain the mortality from these lung-related, breathing-related deaths. And so if any of those explanatory variables there is helpful, we'd like to include it in our model. And then those are the three that we sort of most care about as explanatories. And response is that mortality. Okay, so we have to figure out which variables to use. I got 15. Well, let me just go ahead and count. Let's make sure I have 15 explanatory variables I could consider using. So there's 1, 2, 3. Well, that's hard to count real quick. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way over to precipitation. And 13, 14, 15. So 15 possible explanatory variables. And even ignoring the question of whether we have interactions or quadratics or anything like that, because each variable is either in or not in the analysis. There's 2 states of being for each variable. So there's 15 things that each have 2 different options. So that's 2 to the 15th possible models. And if I remember 2 to the 15th, that's big. I don't remember exactly. So let's do it in my head. because this is like one of those things we learned because that game a few years ago, 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24, 20, 48, 40, 96. Let's just say over 8,000, 17,000, like over 30,000 possible models could be fit. That's a lot of models that we could consider. So which ones should I include and which ones should I not? So conceptually, we should keep in mind categorical versus quantitative variables, categorical factors, if you will. Whether things are linear, get interactions, quadratics, higher order models, model hierarchy. By that, we really mean, yes, use sequential sums of squares and more complex terms belong lower in the table. And then keeping in mind correlated x's, adding a new variable might be helpful, okay? And so we all know a bunch of these tools, okay? We still have yet to tackle, we could even sort of like with residuals and say, oh, here's a transformation that would help, but which variables should I start with? First off, model selection criteria, R squared. Don't use it as a model selection criterion. Literally, by adding an explanatory variable, R squared should go up. The only way for R squared to not go up is if we have a variable which literally has a slope of identically equal to 0. That rarely happens. Or a categorical factor with effects of all 0. Exactly. In a real life data set, that never happens. So basically, the R squared goes up. So maximizing R squared means you're always going to choose every possible explanatory variable, because every time we add one in, things get better. So we don't want to use that R squared. Alternative criteria that people suggest utilizing: minimum mean square error. That's, again, how far we are off in our data points from our fitted equation. So what are the errors? We want small errors, small mean square error. A hack from decades ago, like we're talking 80 years or so, adjusted R square. It's sort of R squared with a penalty term added in. So that way, if you have additional variables, if they don't actually reduce sum of squared errors enough, it actually causes R squared adjusted to go up. To go down. So if you want to maximize adjusted R square, that's a reasonable thing to do, but it's a very old-fashioned thing to do. I mean, that's so last millennium. We don't like that. We do like the idea, though, of penalizing a model for complexity. The more complex a model is, the more I say it really needs to prove itself. That extra complexity, I only want to take that on if it's worth it. So you're thinking a small mean square error relative to the model complexity. That's one thing that adjusted R square tends to do. Another approach, one is CP. It's less popular now than it used to be, but I mention it because the guy who invented it, Colin Mallows, hence Mallows CP. I met him at a party once, and he's one of the few people that I've actually, when opening a bottle of wine, red wine, I spilled all over his sports coat. So a famous statistician, met him at Berkeley, didn't really do much of anything other than spill wine on him. So I feel I owe it to him to bring it up. We don't use Mallows CP a lot anymore, but it has the same flavor as this thing called AIC. AIC, that is the one we tend to like to use as statisticians best. Via a theoretical, well, within the context of one particular theoretical framework, if you choose the model with the smallest AIC value, you're choosing the model that gives you the best chance of estimating slopes that you care about. So that way they're not biased because of the inclusion or exclusion of other X variables. So smallest AIC gives you unbiased slopes. Yay. You don't want biased slopes. If your only goal is prediction, let's minimize something called BIC, Bayes Information Criterion, instead of AIC, Akaike Information Criterion. Maybe it's a little bit better if you're trying to forecast or predict something. This thing called the press statistic, it's in the family called cross-validation. Within cross-validation, the basic idea is we've got a training set and a test set. You've got a big data set, and you take 90% of your data values, you put them in the training set and find the best model out there possible. And then say, I'm going to use my best model from the 90% in my training set, and I'm going to then predict the values in my test set. I'm going to keep track of the errors in prediction, squared and summed. And if I do that for a lot of different possible training sets versus test sets, I mean, I could randomly choose certain 90% of the data points and predict the other 10, and I could do it again, pick another 90% and then forecast the next 10%. If I do that repeatedly through a lot of different 90-10 splits, I'm going to cross-validate my model. I'm choosing the model with the lowest errors when predicting the 10% that's in my test set across all of the possible test sets. Okay, so we tend to like things like that. Okay, a little bit more complex, numerically intensive, but on a computer, we can run that pretty quickly these days compared to when AI adjusted R-square was invented. Again, that's so last millennium. So what should you do? Well, maybe another criterion is only use models where all of the X variables are statistically significant. I don't like that one, but some people use that as a criterion. A way that I like to say it, though, is this: should we include it or not? If that's the game we're playing, X's that you want to test a hypothesis about, include. Okay. If there's a theory in your discipline that says, oh, here's an X that you need to include, include. Yeah, literally not including an X which, according to the theory in your discipline, needs to be included, is a way to possibly bias your parameter estimates. You want to test a hypothesis, you won't be able to do it unless you do include the things you know do better. Okay, what else? Oh, if they've proven themselves worthwhile, if we have a model where we're controlling for these X's, we can explain that other thing. What are the X's we always seem to need to include on our analysis? Because they definitely prove themselves as worthwhile. And then here's the fifth one, or fourth one, that sort of goes against the idea that models where all the terms are significant. I will include even X variables that are themselves non-significant if by including them, I reduce the level of significance, okay, of the variables I care about. If including this new X lowers the p-value on something I really want to investigate, I would include that X as well. And what else? Nothing else. Just don't include. So yeah, if you need it, if you need it, and if it's helpful, include them. Otherwise, don't. And this is all aside from the question of, interactions and transformations and polynomials and all that good stuff that we've dived into recently. Okay, so I used to be, well, shoot, and I'm going to sort of like say, okay, I'm older than you. I remember when maps came on paper, and when maps came on paper, there was this book in the LA area, the Thomas Brothers Guide. Some of you may have parents that are from the LA area and still have a copy of it. And I spent money, $35 to get a Ventura, Los Angeles, and Orange County map. And it was like, 150 pages thick, because on each page, it was a sort of like a zoom in on one little neighborhood. And then you can sort of flip back a few pages and it shows you, well, if you want to be over here at the intersection of 91 and 5, you go to map 8B. So you have to go over to 8B and flip it open. And you see, oh, 8B, that's my thing. And there's like 2 levels of zooming in that they had via this paper map in this book. Okay. These days, when I try and get to places that I haven't been to before, I usually use Google Maps at first when trying to start the process. And actually I was considering just recently, okay, I have to get to Edgewater, Colorado in about a month from now, and I have to drive. Now you're thinking Edgewater, Colorado, how do you get to there? Well, there are a lot of routes that we could take approximately. You might choose the best route from the point of view of speed. Maybe there's the most scenic. Maybe you have a place that you need to stop along the way. But when we first type in, the location, Los Osos, and the other location, Edgewater, Colorado, it gives me this map. Google Maps gives me this, like, I'm not showing you nothing about the details map. It says, oh, here's a blue line you follow. And that blue line that I follow, when I look at it, there are no highway numbers listed. I can almost tell which states I'm going to have to drive through. There's not much detail in that regional level map. Okay. When I, however, get closer to the destination for one particular evening, because there's no way you're driving to Edgewater, Colorado in one day. It's like 24-hour drive time. There's no way you're going to do it in one day. So you're going to have to stop somewhere. Okay. And when you do think, okay, I can make it about this far in a day, and you wonder, okay, I need some food, I have to buy some gas, probably stay overnight somewhere. You try and zoom in a little bit, and that's it at the city level. And then you type into the search hotels, and then it tells you the hotels, and you can see which ones are close to your route, et cetera. Good stuff. And then finally, when you say, okay, I booked the spot to stay overnight, then you sort of say, I want to know what it's like to actually get there. I mean, what exit do I take and what route do I take to get to the hotel from that exit? Okay. So there's that regional view. That's the big picture thing. I'll say knowing which X's you should use of the many possible X's really matters. Second level, if we go down to the city level, if you will, let's actually, look at these model refinements, and that will be like, oh, do I need a quantitative variable times a quantitative variable as an interaction, or do I need a quadratic for a particular trend, et cetera? You can view that as like, oh, I have to adjust to the traffic patterns now. I mean, frankly, if I said, let's drive here to Disneyland, we talked about this earlier this term. There are a lot of different routes that you could take. When a real person is looking at data, when a statistician is looking at data, I'll spot something. My buddy John will spot something else, and my buddy Andrew will spot something else. And we might take different highways on the way to the ultimate destination, but we'll all end up at the same place because hopefully, because we follow the traffic rules and try and drive safe. Okay. So while you may tackle your model refinement a little bit differently than I would initially, you should eventually end up at the same place I do. All good. Then finally, that local view. You want to test a hypothesis about one particular X or several of your X's, just go and do it. Now that you have a good idea of how to get to about where you're supposed to be, and you have a much better idea of the lay of the land with your model having refined it more carefully, then we could answer the questions you really want to answer. So the which X's to use question is really the big picture for the day today. And the methods that we are going to suggest are forward selection, backward elimination, stepwise regression, and best subsets. And I'll say best subsets is usually my favorite, if I can do it. Remember how I said I've got 15 possible explanatory variables? If I included all the possible interactions with our 15 possible explanatory variables and all the quadratics, 15 plus 15, all the quadratics, that's 30 of them. And then all of the interactions, that's 14 times 15 times 14 over 2. So if another 15 times 7, that's okay. And that's the number of variables to either include or exclude. and that's 2 to that power, that's going to be so big that there's no way you're going to have time to fit all the possible models if you include every possible interaction. So forward selection, backwards elimination, stepwise are sometimes useful tools. If you have a big data set, a lot of explanatory variables, stepwise is probably the tool you're going to want to utilize. So let's get towards stepwise, and we're going to do it by describing forward selection first. Forward selection basically says this. Of the 15 possible x's to use in the first step, I want to take the first step that increases r squared the most, or if you will, has the highest model sums of squares, or the lowest sum of squared errors, if you will, or the lowest p-value. They're all about the same. Pick the one best x of the 15. Include that in the model. So we ran 15 regressions to figure out which is the best first term. And now that we've selected that first term, we could have each of our 14 remaining x's could have been included as the second. We got to try 14 more regressions to see who's in the pool number 2. And then after the first 2 best variables are in the pool, we're going to say, well, now which of you remaining 13 is good enough to get in next? And you choose the variable in that third step that maximizes your adjusted or your r squared, minimizes the smallest p-value for that third variable, or maybe the greatest reduction in mean square error, okay? And just continue until you're happy. And your stopping criteria is going to be up to you. One way of thinking is like stop when all of the x variables are with a p-value below 0.05. Boom, done. What about backwards elimination? Backwards elimination is sort of like forward selection, except for, well, we're going the other direction. We've got a model with 15 separate explanatory variables in it, yeah? We could fit it. We ran that regression. And the one variable which is least beneficial with the highest p-value, if you will, get rid of that one. And now we've got a new regression to run. Well, we've got a model with 14 separate x variables in it. We run a regression, get rid of the variable with the highest p-value. Repeat that process, getting rid of the variable with the highest p-value or lowest adjusted sums of squares until you are happy. Backwards elimination tends to take less time. We're fitting fewer models than forward selection. But these two may hit different conclusions. Let me pitch to you a hypothetical data set that I haven't constructed for a class example yet. Okay. If the goal was to predict a person's salary, the salary is their response variable, how much money they take home in a year. The explanatory variables could be age of the person, years of education. So, college degrees, that's 16 years of education. High school degree is 12. And the third variable could be years of work experience. So education, years work experience, and age to predict a person's wage or salary for the year. The first variable that we would pick if we were using forward selection is age. Age comes in first. Age matters the most. And if we then add in the second most influential beneficial variable, which is years of work experience, okay, and then we could put in the third one of education years. Okay, so age first, years work experience second, and then finally years of education. But by the time you put in years of education and years of work experience, between those two variables, they explain an awful lot of what age was initially explaining. The three of them are correlated with each other. I bet you across most people in the US, years work experience plus years of education plus 5 is about what their age is. I could predict age from the other two variables. And because each education and year's work experience is positively related to the response variable of salary, if I were to use just one of those three choices, age sort of works as sort of like a surrogate for the other two taken together. So age is in first if we use forward selection. What if we use backwards elimination? If we use backwards elimination, all three variables are in the model: age, education, and years work experience. Age pops out because it's not barely related to salary at all. It's really the education and the years of work experience that are related to the amount that someone makes, not their age. And so the variable that would be deemed best by forward selection is also deemed worst by backwards elimination. Based on which other X variables are in the model currently, that may impact how a particular X variable is viewed as being beneficial or not. So we like this very method called stepwise regression or stepwise selection. It basically says we're going to start moving forward through the data, and we're going to add a variable and then add another one in, add another one, yet another one, we add more. And if at each step, the variables we've added in so far are able to explain things well enough that one of the earlier variables that we added in early is no longer deemed necessary, we take that earlier one out. It's basically forward selection with elimination as need be. So step forward, and after you take two steps, you keep looking for, after that third forward step, do I have to eliminate any of the previous two that I put in? And again, check for any p-value that drifts above that 0.1 level. And if anything does go above that point level, you kick it out. It's no longer beneficial. So I want to show you how those things could be done inside this example. And it's going to be using that fit model approach. Now, I happen to have put these guys in a particular order. Y first. Why did I put the Y first? Why not? Okay, so yeah, Y variable first, and then the real X variables in parts per million, we're going to ignore them because, again, I've already done a look at the data, and the log version of these works better. So you've got those three X's that probably are important to me to include in my final analysis, then 12 additional ones that may or may not be beneficial. Let's find out if they are. So under analyze fit model, we got our friend, we say mortality, boom, depends on, well, I'm going to just grab them all and say, toss them all in. Now, I'm not going to fit a model with all of them. I, under personality, say, I'm going to go with the stepwise method. Okay, any variable selection method will be found here in stepwise. Okay, and now that I've said, okay, find me the right variables. Okay, stepwise. I'm going to hit run. And now we're given this tool, which I think is sort of cool in a lot of ways. But let's talk how it works. So if your criterion is a certain p-value to get in, or sort of like all the variables have to hit a particular p-value to stay in the model. Okay, no, to get into the model. Maybe you want to go with minimum AIC or minimum BIC. It doesn't really matter which one you want to choose. I'm going to go with AIC for fun. And our forward selection procedure says, well, let's try the first step. Oh, it says non-white percentage is the first variable that pops into our analysis. Let's try another step. Education level pops in second. Third step, log 10 sulfur dioxide. Actually, that's very interesting to me because I know ultimately sulfur dioxide is not that important, but somehow it pops into the model early. Okay. If I were to continue stepping through the model, adding, we keep adding variables, and eventually we have all 15 of them in here. If we had automatically done that by just hitting go and do them all, It would have generated this ordering for me: non-weight first, education second, log SO2 third. I, however, could do my own choice of doing it one at a time. And here is the model. And just for fun, log SO2, the thing that we put in third, log SO2, seems to be not related to the response. So this is maybe one of the situations like I talked about where forward selection may enter something in that ultimately we say, really, we don't want to keep. Okay. If I want to just remove all those, if we want to just automatically do the whole thing, I could just hit go and it would determine for me which one to put in. Like I removed them all, then I'm going to start down here. It puts them in this exact same order as I had done. And it tries to identify the best, if you will, the lowest AIC, well, okay, lowest AIC. So the 601.31, that is the lowest AIC value. So 601.31. Where is it? 601. Hey, there we go. That is the model that the software automatically determines is best via forward selection. What about backwards elimination? I'm going to start over here and say, well, backwards elimination, we're still fitting a model. Recall, stepwise, yeah, like before. I click run to start the process. And instead of forward selection, I'm going to start with backwards elimination, and I got to put everyone in the model to start. And at the first step, I'm going to remove white collar, remove humidity, remove pour, sound, density. I'm removing things. Log 10 SO2 seems to be something that I removed in step 7. It was the third in, and it's the 7th out. We don't need log 10 SO2. I could keep going, boom, 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 until I have a model with no terms in it. And again, via the auto magic criterion of the best, okay, I could just enter all, hit go, and it will do that for me. It's going to say the best model here has an AIC. Did I use AIC? No, we're using minimum BIC as a criterion. So I'm looking for a 611.752. There we go. That is our best model. The model where log 10 SO2, I'm sorry, log 10 hydrocarbons was removed. And so which model is that? We click here to highlight the model. Well, we know we have these 1, 2, 3, 4, 5 terms in it. Whew. Okay, so let's try that auto magic method, best subsets, where we go forward and backwards. And again, boom, start over. And as always, please stop me and interrupt. I know I talk fast. So stepwise. Okay, gonna run. And now I say, well, no, don't use forward selection. Don't use this mixed or stepwise procedure. Again, you can enter a variable in, okay? And as you enter, then eventually one will be ultimately removed. And our stopping rule, the criterion is something like minimum BIC. You could also say there's a p-value threshold. To get in, the p-value must be below 0.25, and to be removed, it must be above 0.25. Let's change these to 0.2 and 0.2, just for fun. And if we automatically do the whole thing, click go. Okay, I can see here we entered in non-white education SO2. Again, the third one in, precipitation, et cetera, and we end up with a model here with the minimum BIC being 615. Yeah, the minimum AIC model is a little bit larger. Okay, has house as well as log 10 NOx. Okay, and so the AIC model, which tends to the minimum AIC model tends to choose a model that's a little bit larger than the minimum BIC model. Not a big deal, but here is the automagic version of this. Forward. And we find here, we did not end up removing this log 10 SO2, even though in my forward, it was the third in, but in the backwards, it was certainly should be removed. Okay. So if we were to change these p-values to get in or out, okay, we might very well have seen something be removed. Okay, so let's try. Let's try 0.1 and 0.1. I'm patient. Remove all. Just automatically do it. Okay, so I didn't hit it. Okay, sorry. Okay, so. I told you that story to tell you this next one. Well, stepwise is great if you have a lot of possible explanatory variables, because you can't literally do every single possible model. Okay, the best subsets doesn't work so well. But if I were fitting my model, and again, recall and under stepwise set of options, run that. I might choose to, instead of using one of these forward or backwards or et cetera, I could say, just fit every possible model, every single possible model. So here we got 15 explanatories. We're going to run 32,000 regressions. And that shouldn't be a big deal because we don't have huge data sets. And furthermore, computers are fast. So this is not too bad. But if you do have enough variables in your model, you will fail. Okay, it'll crap out at you. Your computer will say, I'm sorry, I'm going to freeze. You don't want that. So if you have tried to use best subsets and it says, I'm sorry, that's too big, or it freezes on you, go with forward selection, or better yet, stepwise. Okay, so when I said I want to do all of the possible models, let's cancel that and show you again. All possible models. I'm given a couple options. One is the maximum number of variables to put in a model. Now I'm going to choose to put in 15. Maximum number of explanatory variables. You could put in a different number if you want to. Okay. I pick 15 just because that will produce an ordering of sorts. Okay. And how many models do I want to see? I could look at the best one of any model size. Okay. The best two, the best three, the best four. I'm going to try the best two for now. And we'll look at the output and see how we go. And oh my, hard to work. Blues here, and it alternates blue and white. Blue corresponds to a model of size 1, and the best variable is non-white percentage. If I couldn't use a non-white percentage, but could use any of the others, you would probably choose education level. Its R-squared is higher than any of the other possible choices, besides, of course, non-white percentage. And as we go through the model sizes, we eventually end up with all of the variables are in our model, okay? And we have our R-squared and all of your other fun terms over here off to the right. I don't so much love that. I want to try all possible models, but I'm going to do it again. Rather than 8, I'm just going with like up to a model of size 10, and just show me the one best model, please, of any one model size. Okay. Yes, of course. And so looking across these models here, there's the best model of size 1, best model of size 2, of 3, of 4, of 5, all the way through the best model of 10 explanatory variables. Okay. And on the y-axis in this graph, we can see the RMSE. And if I have just non-white percentage, RMSE is relatively high. If I have education level and non-white percentage, RMSE drops, and it looks like it drops. It seems to keep dropping until we hit like 10 terms. But that's with a fairly complex model. That penalty term takes this curve, which goes down, and makes it bend up a little bit sooner. And so if we are going with minimum AIC, I'm thinking 599.245. That's the model I'm going to stick with for now. My model with only those variables, and which variables are they? Let's look upstairs. Log 10 NOx, precipitation, January temperature, education level, and non-white percentage. That's the model that I'm going to start with before I consider interactions, before I consider quadratics, etc. So here's where the lab differs from the lab I used last time with this exact same data set. I rewrote the lab to say, now that you've figured out which 1, 2, 3, 4, 5 variables, now I've got 5 for my analysis here. In your data set, it's going to be maybe 5 variables, but it's not these variables because it's a different data set. It may choose a number of variables, but what about all the possible ways we could make it fancier? I'm going to do that analyze fit model again. Or here's a cool trick. Notice here that we have these highlighted. You can go up to the top and say, okay, just make a model of those terms exactly. Sort of saves a little bit of time. So I've got mortality depends on all 5 of those x's. So what I want to do is highlight those log 10 NOx, precipitation, that's here. January temperature, right there. Education level, boom. And non-white percentage, there. So I have not included any interactions. I can now do that. Just highlight over here on the left the variables that are automatically selected for me. Under macros, if I say factorial to degree, well, degree 2, it's going to say every pairwise interaction. So for example, log 10 NOx by precipitation, NOx, January temp, NOx, education, NOx, non-white, precipitation, January temperature. Every single one of the possible interactions was included. And I could take my friends here again, log 10 NOx, precipitation, oh shoot, highlight, and then right click, mouse down, precipitation, January temperature, education level, and non-white percentage. I can also choose to add all of the quadratics by, again, degree of 2, a polynomial to degree 2. And down there at the bottom, you see, you know, precipitation squared, January temperature squared, education squared. Now, if I were to, again, try stepwise as a procedure, a collection of procedures, and run, it says you could include any one of these terms or perhaps not include them. Which ones are you going to want to use? Well, there's a lot of possible terms to include or not. I want a little bit of help. I'm just saying, try all possible models. I could use forward selection or backwards elimination, but let's just go ahead and try all possible models. And how many terms do I want them all? Well, let's go up to 12 of them. For fun, let's do up to 12. But only show me the best one variable or one best model per number of variables. So of all the possible models of 5 variables, just show me one, the one that's best. So the best model of size 1, 2, 3, all the way up through the best model of size 12 is what I should be receiving. And now, do y'all spot this? Restrict models to where interactions imply lower order, blah, 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 blah. That's called model hierarchy. If you have a model with an interaction in it, only allow that interaction to be included if each of the 2 main effects are first included. Now, that is something that I know statisticians will argue about. I tend to like it for the sake of interpreting parameters. People who are more focused on prediction tend to not select this option, and they get what they get, and they end up doing usually about the same thing anyway. Okay. Click OK. Okay, so well, shoot, this is a pain in the ass because look at this, it's really wide. So it's like 2 screens wide to even read it. But we can see if we have a model with 1 term, 2 terms, 3 terms, 4 terms, then 5 terms, those are the 5. Those were put in a linear fashion first. But once we have the model with 5 terms in it, the next term is, well, let's take non-white and square it. Non-white squared is that 6th variable that we could include. And if I like my minimum AIC criterion, I'm going to go with a 594. 594.476. That seems to be the model that is nominally best from the point of view of minimizes AIC. Okay, so the model that we like best has 1, 2, 3, 4, 5, 6, 7 terms in it. The 1, 2, 3, well, actually, hold on a second. Log 10, and so January temperature, which we earlier thought mattered, no longer matters. Log 10 NOx times precipitation seems to be in there. Education squared is in there. Non-white percentage is in there, squared. This is the model that is deemed best. Okay, so what would I do? I'd probably go ahead and make that model, and with standard least squares, run it, fit it, and start the process of looking at residuals. Are they normal? Do we have equality of spread? Do I need to fix something? And then I would perhaps include even the X variables that we had not originally considered in our second round. Remember how we had our January temperature variable? January temperature somehow magically disappeared because with these other guys in there, January temperature is no longer needed. But over 65, because of these inclusion of these exact terms, maybe over 65 will pan out. It's possible. So we'd have to plot the residuals against each of the X's just to see if that's an X that would matter and needs to now be entered in yet again. Okay, so that's the basics on model building. The real idea is lather, rinse, and repeat. You've seen that, heard the joke about how do you trap a computer science major? You ask them to take a shower and hand them the shampoo bottle and ask them to read the instructions. Lather, rinse, repeat. Then they lather, rinse, and then repeat. And they repeat the repeat, which is lather, rinse, and repeat. That was funny, damn it. Okay, so that's what this feels like. We're using one of these methods to just pick some of the variables. And we look for whether there's problems, interactions, quadratics, et cetera. And we fit a model, we look for problems, refit, look for problems, refit, look for problems, using these tools, all of the tools we have so far. And eventually, we're going to get all to the same place. So again, I think I've maybe mentioned this to you in a past class, but I certainly hinted at it earlier. If I said I'm going to meet you at Choro and Haigara in 2 hours, some of you are saying, dude, I'm in China, I can't. But whatever. If you are within an hour drive of Slow and I say I'll meet you at Choro and Haigara in 2 hours, even if we are all in the exact same classroom, we would probably choose different routes to get there. As long as our route is reasonable, we should end up at the same place, yeah? As long as we're following the rules of the road, the traffic rules, we should all get to the same place. In that same sense, different people who utilize the rules in slightly different orders, we tend to always arrive at similar outcomes. Maybe my final model is not the exact same as Andrew's, but it's going to be close enough that we're answering the same question in approximately the exact same way. Okay, good place to stop. I will tackle questions you might have and stop the sharing. And any questions before we take a quick break and I come back to office hours in 8 minutes? So I'm going to stop the recording then, and I'll pop over to office hours.